Understanding how researchers investigate sugar's effects on brain health requires familiarity with the diverse measurement tools employed across epidemiological, clinical, and basic science studies. These biomarkers collectively enable scientists to trace pathways from dietary exposure through metabolic changes to cognitive outcomes. Blood-based markers provide accessible metabolic snapshots. Hemoglobin A1C measures average blood glucose levels over preceding months, offering superior insights compared to single glucose measurements. Elevated HbA1c indicates chronic hyperglycemia, the metabolic foundation for many downstream brain effects. Fasting insulin and glucose enable calculation of insulin resistance indices like HOMA-IR, quantifying how efficiently cells respond to insulin signaling. Inflammatory markers including C-reactive protein, interleukin-6, and tumor necrosis factor alpha reflect systemic inflammation that may affect brain tissue. While not specific to neuroinflammation, these peripheral markers correlate with cognitive decline in longitudinal studies and provide practical measurement opportunities impossible with direct brain sampling. Advanced glycation end products represent another blood-based measure. These molecules form when sugars bind proteins, accumulating with chronic hyperglycemia and directly damaging tissues, including neurons. Specialized assays quantify Ag levels, though standardization remains challenging. Neuroimaging technologies enable direct brain assessment. Structural MRI measures brain volume and detects atrophy in regions vulnerable to metabolic dysfunction, particularly the hippocampus critical for memory. Functional MRI reveals brain activation patterns during cognitive tasks, with altered patterns indicating dysfunction. PET scanning using specific radiotracers can visualize amyloid and tau protein accumulation, the pathological hallmarks of Alzheimer's disease. More specialized imaging includes measures of microglial activation indicating neuroinflammation and assessments of brain glucose metabolism revealing how efficiently different brain regions utilize fuel. These advanced techniques remain primarily research tools given cost and limited availability. Cerebrospinal fluid analysis, while invasive, provides biochemical windows into brain pathology. CSF levels of amyloid beta, tau proteins, and neuroinflammatory markers enable earlier detection of neurodegeneration than clinically apparent symptoms allow. Some studies correlate peripheral metabolic dysfunction with altered CSF biomarkers, strengthening mechanistic connections. Cognitive assessment batteries translate biological changes into functional outcomes. Validated neuropsychological tests measure memory, attention, executive function, processing speed, and other domains. Standardized administration enables comparison across studies and detection of subtle changes preceding dementia diagnosis by years. Longitudinal study designs prove essential for establishing temporal relationships. Single time point measurements reveal associations, but cannot determine whether metabolic dysfunction precedes cognitive decline or vice versa. Cohorts following thousands of individuals across decades enable tracking how midlife sugar intake and metabolic patterns predict late-life cognitive outcomes. Multimodal approaches combining diverse biomarkers strengthen causal inference. When studies show that high sugar intake associates with elevated HbA1c, which associates with increased inflammation, which associates with accelerated brain atrophy, which associates with cognitive decline, the convergent evidence across biological levels supports mechanistic pathways rather than spurious correlation. Study limitations involve measurement challenges and confounding. Blood markers fluctuate with recent intake, potentially missing longer-term exposure patterns. Imaging detects changes only after substantial pathology accumulates. Cognitive tests show practice effects and cultural biases. Residual confounding from unmeasured variables constantly threatens observational research. Nevertheless, the expanding biomarker toolkit enables increasingly sophisticated research connecting diet to brain health. As technologies improve and costs decrease, researchers can assess mechanisms in larger cohorts with greater precision. The convergence of evidence across multiple biomarker types, metabolic, inflammatory, neuroimaging, and cognitive, progressively builds understanding of how dietary patterns influence brain aging. For clinicians and public health practitioners, biomarker research translates to concrete recommendations even while mechanistic details continue emerging. The consistent patterns linking poor metabolic health to cognitive decline across diverse measurement approaches justifies preventive dietary guidance. Meanwhile, for scientists, the expanding toolkit enables testing specific hypotheses about biological pathways, potentially identifying intervention targets beyond simple sugar reduction.